Hi everybody, my name is Aleksa Stefanovic, and today I'll be presenting my review of the paper AI Programmer autonomously creating software programs using genetic algorithms by Becker and Gottstich. So another reason why I chose, one of the main reasons why I chose this paper and found it interesting is because I am finishing my degree now in software engineering with a concentration in AI. So this kind of ties everything together. And also this paper explores a very interesting idea whether a system can automatically generate software programs entirely on its own using evolutionary algorithms. So instead of humans writing code, we have the computer that evolves the program over time. So the core idea of the paper is to use genetic algorithms, or I'll mention them GA for short, to evolve complete working programs. So the author designed a minimal 8 instruction programming language to dramatically shrink the search space, allowing evolution to be computationally feasible. So the process is simple in concept. The system generates an initial population of random programs, scores them with a fitness function, and then uses selection, crossover, and mutation to evolve them into a better program or programs over many generations. So, why this approach? The motivation behind this system is that human-written software is expensive, time-consuming, and requires expertise, preferably higher expertise, to get the complete setup. So a GA can automatically explore thousands of potential solutions without human intervention. However, normal programming languages are far too large for evolution in search, so the authors minimize the language to allow evolution to work efficiently, safely, and to get good results. So, system architecture. So the system architecture has a few major components. The first one is genome representation. Every program is encoded um, as an array of floating point values between 0 and 1. Each gene maps to one instruction in the 8 instruction language, which reduces significantly the complexity of the program. Another thing is instruction mapping. The range 0 to 1 is divided uniformly into segments. Each segment corresponds to an instruction. Third, embedded interpreter. So this is a pretty cool thing. Instead of running programs directly on the machine, all evolved code is executed in a secure interpreter. This prevents crashing, freezing, or even unsafe behavior by the algorithm and program. And the last thing is fitness evolution. So, not evolution, evaluation, I apologize. So after running the program, the system calculates a fitness score based on how close the output is to the target. And we have done this in our previous assignments and examples in class. So, yeah, and next, let's look at the GA components directly. So the genetic algorithm includes a population of candidate programs, roulette wheel selection to choose parents, crossover to combine different genes, mutation to introduce variability, and also I can also mention this as a part of it is replacement to build upon to the next generation. So over time, the program that performs the task better and better are more likely to survive and continue on, as they say, reproduce later into different better variations of the program. And another, I would say, key detail is that early in the process, most generated programs won't work at all. They'll mostly fail. They'll either crash, loop forever, or produce nonsense. To address this, the authors actually used controlled mutations and equal gene mapping so that all instructions are equally likely. And without this fairness, some instructions could dominate the genome and prevent the system from evolving useful patterns and down to their children, as they say, or better versions of themselves. So, example of genome mapping. In this example, each floating point value maps clearly to one instruction in the eight instruction kind of language that they built, and these include moving the pointer, modifying the byte value, input and output, uh, and I'm forgetting one, simple logs. Not logs, simple loops. I apologize. So these are kind of the main things that the language is actually kind of Turing complete, which means it can theoretically express any computable program, even though it's very, very simple. Uh, and some of the strengths, of course, of this approach, which I mentioned previously, is one second. Let me see. Yeah, I thought the slide already went. So, I mean, the paper explains the system clearly and logically. So everything makes sense, and it's, I'm not going to say simple, but it is very readable and understandable, which is very important. The interpreter adds safety and scalability and some point of control to the whole program. And the minimal instruction set that I mentioned previously significantly reduces the search space and the whole complexity. And this allows us to use this on any CPU or normal CPUs. You don't need any extra equipment or even hardware to do this. And that is actually maybe one of the best things to mention. Uh, and lastly, I'm trying to think. Lastly, yeah, the replacement to build upon to the next generation, which over time the program performs the tasks better and better, and yeah, that would help. How should I say, facilitate better survivability of the programs because of the earlier method mentioned to keep it kind of structured in a way so not all in the beginning programs fail. So let's go to limitations. So we mentioned some strengths, some cool stuff. So the main limitations here, the system struggles to scale beyond the simple program. So that is a big trade-off, but in the long term, maybe somebody will find a better way or solution. So the evolved programs tend to be very short and basic, which is explained by the 8-bit, the new language that they've created. The search still produces also many invalid programs in early generations, which is an issue, but they addressed it accordingly. And the fitness function must be manually designed for each task that's needed. I mean, this approach is not yet suitable for real-world software development, but uh, who knows in the future how things might evolve. So all of these limitations that I mentioned, I think the main point I would say is that scalability is really the biggest challenge and the biggest issue as problems become more and more complex. The genetic algorithm, or GA, needs exponentially more generations to discover useful code, and this would evolve it into needing more space, more hardware, stronger CPUs, and so forth. So experimental results. So in the results section, the authors show examples of evolved programs that successfully perform tasks, like outputting, for example, text such as hello. They use as an example. These examples are very simple, like I mentioned, but they show that the concept of evolving programs by itself works. The system evolves from random garbage to meaningful programs through natural selection, which is kind of the main point of this experiment and the paper. What's interesting to watch is the progression over generations. So early generations produce random, non-functional responses. Then the GA starts discovering useful building blocks, let's say short loops, increments, pointer movements, and ultimately assembles them into a working sequence that creates a working program, even though it is simple. This actually mirrors natural evolution perfectly. Starts with randomness, apply a little bit of pressure, gradually improve structure, and eventually reach functional complexity. Okay, so let me critique a little bit this whole paper. So overall, the paper is both innovative and practical. It offers a fresh take on these autonomous program uh, creations or synthesis. And although it's limited in scope, it lays an important foundation for future work. Like I said, simple programs, simple language, but in the future, people can build upon and create more complex and harder languages and more complex programs. I mean, some programs that evolve to a very high complexity, which I think will be really, really cool. The biggest missing piece, in my opinion, is the comparison to other techniques like genetic programming or symbolic analysis. But given the novelty of the system, I would say the contribution is still really, really strong. So not a lot really to uh, to to critique it. And also now let's go into future improvements. Future directions I would mention could include adaptive mutation rates, better fitness templates, combining DGA with natural language models, using static analysis to filter bad candidates, and expanding the instruction set in controlled ways. So there's more options. I think that these kind of additions would help the system scale and be more complex in its tasks. And finally, to conclude, to wrap everything up, the AI programmer paper demonstrates that GAs or genetic algorithms can evolve complete working programs when the language and environment are carefully designed. So in its early stage system, uh, I mean, it is an early stage system, but it shows great promise for future work and for the future of automated software creation and search-based software engineering. Um, uh, Thank you so much for listening to this presentation. Hopefully you learned a little bit something about the paper. And yeah, if you have any questions, shoot me an email or message me on Teams. Wish you all the best and have a wonderful holiday next week, Thanksgiving. Bye.